In our experience, things don't really ever come to a definite end. When we die, our bodies break down, and the stuff they're made of goes back into the earth and air, helping new life form. So, in a way, we live on through what happens afterward. But could there be a time when there's no after anymore? Sadly, according to modern physics, that could happen. Time itself might stop. Everything would freeze, and there wouldn't be any more new beginnings or recoveries. The end of time would mean the end of all endings. This scary idea wasn't something people thought about before Einstein's theory of relativity, which explains gravity in modern science. Before that, most scientists and thinkers believed that time was like a steady beat that the universe followed without changing. But Einstein showed that the universe is more like a big musical jam session with different rhythms. Time can slow down, speed up, or act in unexpected ways. When we feel gravity pulling us, we're actually experiencing time moving at a different pace. Objects fall toward areas where time moves more slowly. Time doesn't just pass, it reacts to what's happening around it, like musicians playing together in a lively rhythm. But sometimes things can get chaotic, and time can seem to vanish, like a drummer getting too carried away and burning out. When time reaches its limits, scientists call those moments singularities. These can mark the start or end of time itself. The most famous singularity is the Big Bang, which happened around 13.7 billion years ago, kicking off the universe and time as we know it. If the universe ever stops expanding and starts collapsing, it could lead to a reverse of the Big Bang called the Big Crunch, where time would stop. However, time doesn't necessarily end everywhere. Inside black holes, according to relativity, time comes to an end while it continues outside in the universe. Black holes are notorious for their destructive nature, but they're even more extreme than commonly thought. If you were to fall into a black hole, not only would you be torn apart, but eventually you'd reach a point called a singularity at the center, where your timeline would cease. There'd be no rebirth from your remains. They wouldn't be recycled. It's like reaching the end of a story, not just facing death but experiencing an existential collapse. Physicists wrestled with the unsettling idea that relativity predicts such a grim fate without any hope of renewal. Even today, they're not entirely sure how to interpret it. Singularities are a major reason why physicists aim to develop a unified theory of physics, blending Einstein's theory with quantum mechanics to create a theory of quantum gravity. Part of this effort is driven by the hope of explaining away singularities. However, this pursuit comes with caution. While the end of time is hard to fathom, the idea of time not ending might be equally puzzling. Before Albert Einstein's contributions, philosophers had long debated whether time could have an end. Immanuel Kant saw it as an antinomy, a concept with arguments on both sides, leaving people uncertain. In philosophical terms, an antinomy refers to a situation where both sides of an argument have seemingly valid and contradictory points, leading to a state of uncertainty. Kant, recognizing the complexity of the concept of time, saw it as a topic that could give rise to conflicting perspectives. On one hand, arguments could be made suggesting that time is infinite and continuous, without any conceivable end. On the other hand, there were compelling arguments proposing that time might have limitations or a conceivable endpoint. Aristotle also grappled with this idea, suggesting that time couldn't have a beginning or an end. Each moment marks both the end of one period and the beginning of another. Every event is both caused by something and leads to something else. So, how could time ever come to a halt? What would stop the last event from leading to another? Moreover, how do you even define the end of time when end itself relies on the concept of time? Oxford philosopher Richard Swinburne argues that it's logically impossible for time to end. But if time is endless, then the universe must exist infinitely, raising complex questions about infinity that philosophers have found challenging to grasp. The acceptance of the Big Bang theory and the discovery of black holes initially seemed to provide answers. They suggested that the universe could face various catastrophic scenarios, from the Big Crunch to the Big Rip, Big Freeze, or Big Break. However, understanding what singularities truly are has become less clear. Lawrence Sklar, a prominent philosopher of physics at the University of Michigan, notes that the physics of singularities remains uncertain and open to interpretation. The very theory that gives rise to these phenomena suggests they might not truly exist. For instance, in the case of the Big Bang singularity, according to relativity theory, all the material that eventually formed every galaxy we observe today was compressed into a single mathematical point, a point with zero size. Similarly, within a black hole, every particle of an unfortunate astronaut object is squeezed into an incredibly tiny point. In both scenarios, the calculations lead to dividing by zero volume, resulting in infinity. There are other types of singularities where infinite aspects come into play, although not necessarily infinite density. While modern physicists don't shy away from infinity as much as Aristotle and Kant did, they still see it as a warning sign that their theories might be reaching their limits. Take the standard theory of ray optics taught in school, for example. While it beautifully explains things like eyeglass prescriptions and funhouse mirrors, it predicts that a lens focuses light from a distant source into a single mathematical point, creating a spot of infinite intensity. However, in reality, light focuses on a bullseye pattern, and its intensity, while high, is always finite. This discrepancy arises because light behaves more like a wave than a ray. Similarly, most physicists assume that cosmic singularities actually have a finite, albeit very high, density. They believe that relativity theory fails to fully capture some important aspects of gravity or matter near singularities, which would otherwise keep the density in check. Physicist James B. Hartle of the University of California, Santa Barbara, notes that many would agree that these singularities indicate where the theory breaks down. Understanding what happens in these extreme scenarios requires a more comprehensive theory, namely a quantum theory of gravity. Physicists are still developing such a theory, but they anticipate it will incorporate a fundamental insight from quantum mechanics. That matter, like light, exhibits wave-like properties. These properties should blur the supposed singularity into a small bundle rather than a point, eliminating the mathematical error of dividing by zero. If this holds true, time might not come to an end after all. Physicists debate both sides of the argument. Some believe that time does indeed end. However, this poses a challenge because the known laws of physics operate within time and describe how things move and change. Endpoints of time would require not just a new law of physics, but an entirely different type of law, one that doesn't rely on temporal concepts like motion and change, but instead emphasizes timeless principles such as geometric symmetry. For instance, Brett McInnes of the National University of Singapore proposed an idea based on string theory, a leading contender for a quantum theory of gravity. He suggested that the early universe may have had the shape of a torus, a donut-like structure. Mathematical theorems about tori dictate that it must be perfectly uniform and smooth. However, at a big crunch or black hole singularity, the universe could take on any shape, and the same mathematical principles might not apply. The universe could be extremely irregular. Such a geometric law of physics differs from traditional dynamic laws in a crucial aspect. It lacks symmetry in time. In this scenario, the end wouldn't simply be the beginning played in reverse. Other researchers in the field of quantum gravity believe that time stretches endlessly, without a beginning or an end. They see the Big Bang as merely a significant transition in the ongoing life of the universe. According to this perspective, the universe might have started contracting in a big crunch before rebounding when the density became too high, a phenomenon known as a big bounce. Traces of this prehistoric era might still exist today. Similarly, they suggest that the singular bundle at the core of a black hole might behave like a miniature star, boiling and bubbling. If you were to fall into a black hole, while it would be a painful end, your timeline might not cease entirely. Instead, your particles would enter the bundle, leaving a distinct mark that future observers might detect in the faint light emitted by the black hole.
If you're creating content that stands out, you are not looking for just music. You are looking for great music.
By proposing that time continues indefinitely, proponents of this view avoid the need for speculation about a new type of physical law. However, they encounter their own challenges. For example, the universe tends to become increasingly disordered over time. If it has existed forever, why isn't it completely chaotic by now? Additionally, how could the light carrying your imprint escape the intense gravitational pull of a black hole? The struggle with paradoxes in understanding time is not unique to physicists. Philosophers have grappled with similar issues for centuries. John Archibald Wheeler, a prominent figure in quantum gravity, famously remarked, "Einstein's equation says this is the end, and physics says there is no end." Faced with this conundrum, some people conclude that science may never definitively resolve whether time has an endpoint. For them, the boundaries of time are also the limits of reason and empirical observation. However, others remain optimistic, believing that with innovative thinking, physics can eventually provide a clear answer. Physicist Gary Horowitz of UC Santa Barbara asserts, "It is not beyond the realm of physics. Quantum gravity should be capable of providing a definite solution." As physicists and philosophers grapple with the concept of the end of time, many draw parallels with the end of life itself. Just as life emerges from inanimate molecules organizing themselves, time might arise from some timeless substance that self-organizes. A world with time is one with intricate structure. Time helps us understand when events happen, how long they last, and their sequence. Perhaps this structure isn't imposed from outside, but rather emerges from within. Just as what's built can be dismantled, when this structure breaks down, time ceases to exist. According to this perspective, the end of time is no more perplexing than the breakdown of any other complex system. Gradually, time loses its defining characteristics and transitions from existence to non-existence, much like passing through twilight. The first aspect of time that might disappear is its one-way directionality, the arrow pointing from the past to the future. Physicists have understood since the mid-19th century that this arrow is not an inherent property of time itself, but rather a characteristic of matter. Time inherently flows in both directions. The arrow we perceive is simply the natural progression of matter from order to disorder, a phenomenon familiar to anyone who lives with pets or young children. This initial orderliness may stem from the geometric principles proposed by McInnes. If this trend continues, the universe will eventually reach a state of equilibrium, known as heat death, where it cannot become any more disordered. While individual particles will continue to rearrange themselves, the universe as a whole will stop changing, and any remaining clocks will oscillate in both directions. The distinction between the future and the past will blur. Some physicists have speculated that the arrow of time might reverse, causing the universe to tidy itself up. However, for mortal beings whose existence relies on a forward arrow of time, such a reversal would signal the end of time as surely as heat death would. Recent research suggests that along with the arrow of time, another fundamental aspect that time might lose is the concept of duration. In our current understanding, time is measured in units like seconds, days, and years. Without these units, we could still perceive events occurring in chronological order, but would be unable to determine their duration. This idea is proposed by University of Oxford physicist Roger Penrose in his book, Cycles of Time, An Extraordinary New View of the Universe. Throughout his career, Penrose has been deeply interested in the nature of time. In collaboration with physicist Stephen Hawking in the 1960s, he demonstrated that singularities, points of infinite density, should be a common feature of the universe, not just in special circumstances. Additionally, Penrose has argued that matter falling into a black hole ceases to exist in any meaningful sense, and that time might not play a role in a truly fundamental theory of physics. In his latest work, Penrose starts by examining the early universe. At that time, it resembled a disordered collection of particles, much like a box of Legos scattered on the floor awaiting assembly. This chaotic mix included quarks, electrons, and other elementary particles. From this chaos, structures like atoms, molecules, stars, and galaxies gradually formed, one step at a time. The first significant step occurred about 10 microseconds after the Big Bang, or Big Bounce as some theories suggest. This step involved the creation of protons and neutrons, each consisting of 3 quarks and measuring about a femtometer across. Prior to this event, there were no coherent structures. Nothing was composed of bound-together pieces. Consequently, there was no framework for timekeeping. Clocks rely on a stable reference, such as the length of a pendulum or the size of atomic orbitals. However, at this early stage, no such reference existed. While clumps of particles may have temporarily formed, they lacked a fixed size and thus couldn't serve as a reliable time reference. Even individual quarks and electrons, the building blocks of matter, have no discernible size when closely examined. They appear as mere points to particle physicists. The only attribute resembling size is their Compton wavelength, which determines the scale of quantum effects and is inversely related to mass. However, even this rudimentary scale was absent before a time of about 10 picoseconds after the Big Bang, when the process responsible for imparting mass had yet to occur. There's no way to keep track of time, Penrose explains. Without anything capable of marking regular time intervals, whether an attosecond or a femtosecond passes makes no difference to particles in the primordial soup. Penrose suggests that this scenario not only characterizes the distant past, but also the distant future. Even after all the stars have faded away, the universe will be left with a bleak mixture of black holes and free particles. Eventually, even the black holes will decay, leaving only the particles behind. Most of these particles will be massless, like photons, rendering the construction of clocks impossible once again. In alternative scenarios where the universe ends in events like a big crunch, clocks wouldn't fare any better. You might think that duration would still exist conceptually, even if it couldn't be measured. However, researchers question whether a quantity that cannot be measured, even in theory, truly exists. To them, the inability to build a clock suggests that time itself has lost one of its defining features. If time is what is measured on a clock and there are no clocks, then there is no time, says philosopher of physics Henrik Zinkernagel of the University of Granada in Spain, who has also investigated the disappearance of time in the early universe. Despite its elegance, Penrose's scenario has its weaknesses. Not all particles in the distant future will be massless. Some electrons will likely survive, and it should be possible to construct a clock using them. Penrose suggests that electrons might somehow lose their mass, but he admits this idea is speculative and uncertain. That's one of the more problematic aspects of this theory, he acknowledges. Additionally, if the early universe lacked a sense of scale, how did it manage to expand, thin out, and cool down? However, if Penrose's theory holds true, it has a remarkable implication. Despite appearing vastly different, with one being densely packed and the other ever emptying, both the early universe and the remote future lack clocks and other measures of scale. The Big Bang resembles the distant future very closely, Penrose notes. He boldly suggests that they might actually represent different stages of a grand cosmic cycle. According to this idea, when time reaches its end, it will loop back around to initiate a new Big Bang. Thus, Penrose, who has spent his career arguing that singularities mark the end of time, may have discovered a way to perpetuate it. The supposed slayer of time has become its savior. Even if duration loses its meaning and femtoseconds and attoseconds blend together, time is not entirely extinguished. It still governs the sequence of cause and effect, unlike space, which allows for various arrangements of objects within it without imposing a specific order. Events that occur sequentially in time, like typing on a keyboard and seeing letters appear on a screen, are inherently connected. However, spatial relationships between objects, such as a keyboard and a post-it note, may be unrelated. Under certain circumstances, time could lose even its basic ordering function and become akin to another dimension of space. This idea traces back to the 1980s, when Hawking and Hartle proposed that the Big Bang marked the differentiation of time and space. Inspired by string theory, which suggests that our universe may be a membrane floating in higher dimensional space, these researchers theorized that under specific conditions, time could merge with space. Imagine our universe as a leaf floating in the wind, with us trapped on it like caterpillars. While normally we can move around freely in our four-dimensional prison, if the leaf is buffeted about vigorously enough, we become immobilized. To make any progress along the membrane, we would need to travel faster than the speed of light, which is impossible. Consequently, all processes cease, as they all require some form of movement, which becomes unattainable. Viewed from an external perspective, our life's timelines, formed by successive moments, don't actually come to an end, but instead curve, becoming lines through space. In this scenario, the membrane, brain, remains four-dimensional, but all four dimensions become spatial dimensions. Objects are compelled by the brain to accelerate closer and closer to the speed of light until their trajectories become superluminal, effectively eliminating time. Importantly, individuals experiencing this transformation might be unaware of it. Since all clocks would slow down and stop, we wouldn't realize that time was transitioning into space. Instead, we would observe objects like galaxies appearing to accelerate, a phenomenon often attributed to dark energy by astronomers. However, could this acceleration actually signal the transformation of time into space? At this advanced stage, it might seem that time has vanished completely. Yet a semblance of time persists. Even if we can't define duration or causal relationships, we can still assign events to specific points in time and arrange them on a timeline. Recent advancements by groups of string theorists explore how time might lose this last remaining characteristic. They investigate what happens to time at black hole singularities using one of string theory's fundamental concepts, the holographic principle. A hologram is a unique type of image that creates an illusion of depth. Despite being flat, it appears as though a solid object is suspended in 3D space. The holographic principle suggests that our entire universe operates like a holographic projection. In this analogy, a complex system of interacting quantum particles can create a perception of depth, adding an extra spatial dimension that isn't inherent in the original system. However, not every image can be a hologram. Specific patterning is required. If a hologram is damaged or scratched, the illusion is ruined. Similarly, not every particle system can generate a universe like ours. The system needs precise patterning. When the system lacks the necessary regularities initially and then develops them, a spatial dimension emerges. Conversely, if the system loses its orderliness, the dimension disappears. Consider the collapse of a star into a black hole. While the star appears three-dimensional to us, it corresponds to a pattern in some 2D particle system. As the star's gravity increases, the corresponding flat system vibrates more intensely. When a singularity forms, order breaks down entirely. This process is akin to the melting of an ice cube. The orderly arrangement of water molecules transforms into the chaotic disarray of a liquid. Hence, the third dimension essentially dissolves away. As the spatial dimension melts away, time follows suit. If you were to fall into a black hole, the time displayed on your watch would vary depending on your distance from the center of the hole, which is determined within the collapsing spatial dimension. As this dimension disintegrates, your watch would begin to spin uncontrollably, making it impossible to pinpoint when events occur or where objects are located. The conventional geometric concept of spacetime ceases to exist.
Obtén un correo electrónico profesional con GoDaddy. Imagina que recibes dos
In practical terms, this means that space and time no longer provide a framework for understanding the world. Attempts to measure the positions of objects reveal that they seem to occupy multiple locations simultaneously. Spatial distances lose their meaning, as objects can seemingly teleport from one place to another without traversing the space in between. This phenomenon even allows the imprint of an unfortunate astronaut who crosses the black hole's event horizon, the point of no return, to escape back out. If space and time vanish near a singularity, the event horizon loses its clear definition. In essence, string theory doesn't just smooth out the hypothetical singularity, replacing it with a more acceptable concept while leaving the rest of the universe unchanged. Instead, it reveals a broader breakdown of the ideas of space and time, whose effects extend far beyond the singularity itself. However, the theory still relies on a fundamental notion of time within the particle system. Scientists are currently striving to develop a concept of dynamics that doesn't assume the existence of time at all. Until then, time stubbornly persists. It's deeply ingrained in physics, and scientists have yet to envision its complete disappearance. Science tackles the incomprehensible by breaking it down into manageable steps. The same applies to the end of time. Reflecting on time leads to a deeper understanding of our place in the universe as mortal beings. The qualities that time will gradually lose are essential for our existence. We rely on time's unidirectionality for development and evolution, duration and scale for building complex structures, causal ordering for processes to unfold, and spatial separation for creating pockets of order in the world. As these qualities erode, so does our ability to thrive. While we can envision the end of time, no one will directly experience it, much like how we cannot be conscious at the moment of our own death. As our distant descendants approach the end of time, they will face increasing challenges in a hostile universe, and their efforts will only accelerate the inevitable. We are not passive victims of time's demise. We contribute to it. Through our existence, we convert energy into waste heat, contributing to the universe's degeneration. Time must cease for us to continue living. And that's it for this video. Thanks for watching. You can watch my video about time paradoxes on your screen, and I'll see you there.
the strangely blinding effect of certain things, certain little events that blind us to the possibilities, to the alternatives. We have tried to study already this process. Let me mention one early experiment performed at MRI, and it was supposed to explore a little bit how people get into this kind of no-exit situation. You may have heard the example, bear with it please, it bears repeating. It is Dr. Jackson, it involves Dr. Jackson, who, as you probably know, was an internationally known expert on the psychotherapy of schizophrenia. And we asked him one day if he was willing to have himself filmed in a first interview with a paranoid patient whose main delusion was to be a clinical psychologist. And Dr. Jackson agreed to this, and we then went to the VA in Menlo Park, and where we knew a clinical psychologist who also did the therapy of schizophrenics. And we asked him if he was willing to have himself filmed in a first interview with a paranoid patient whose main delusion it was that he was a psychiatrist. And then we brought the two learned doctors together in a kind of a super therapy session in which both promptly began to treat each other. And the more mental health and reason and therapeutic endeavors they injected into the situation, the crazier they appeared to the other, of course. And I must say, this experiment has always been on my mind and has influenced a great deal of what I am doing.